All right, welcome back. Chapter 13, Part 2. This time we're going to be talking about the energy in the coupled circuit. You may recall the work or the energy stored in an inductor. It's capable of storing things. Storing energy was work is 1/2 Li squared. All right, but now we're going to look at two coils with some mutual coupling. And so this is the circuit that we'll be analyzing. And notice the dot convention. The left side we'll call the number 1 side, the right side number 2, and the currents are entering from the top and voltages are positive at the top. So let's begin. Very similarly, the power, we're going to begin with power V1I1 squared on the left side. We're going to do this analysis, but to do this well, we're going to be modifying both of the currents a little bit. So let me set up here. I'm going to call this the I2 current up here, the I1 current down here, time, of course, going in this way. All right, in the first step, I1 is going to be increasing. Doesn't matter, this is sort of a lumpy linear. It doesn't matter that it's linear. The important point is that it is increasing while I2 is staying with no time change, right? So di dt is 0 here, right? Di dt equals 0. And here there is, down here with I1, there is a positive di dt. So during that first step, if we integrate the power over time, it turns out we are doing what? We are integrating I di over the rise of I1 from 0, I should have used, to a peak value of I1. All right, because we took the power here, right, what did we do? We took this expression, multiplied it by dt, so the dt is gone, right? And then integrate, so we're left to integrate over I, not over time. We've seen all this before, and we end up with this, 1/2 Li squared. All right. Now, the power on the second side, we're going to go back over to our current here, and we're going to hold I1 steady. Now, the importance of this steadiness is if there is no change, no di dt, then there was no mutual coupling on the first side right here, right? There's no change in di dt, so there was no mutual coupling back. And that's why this formula up here ended up so simple. All right, so now we're down here, and we're going to be in the same fashion, lifting I2, but holding this steady. So now we've got di dt here equals 0. All right? So this is going to be region 1. This will be region 2. And when we get to it, this will be region 3, of course. But so let's stay. We're in region 2. And now I1 is not time changing. It's not 0, but it's not time changing, right? So what does that mean? Any contribution, such as we saw here, due to time, will not be happening because this factor, di dt, will be 0 in region 2. Okay? So let's go on from there. This is our power. There is a mutual component. This is what? Side number 2 coupling back to side 1. Right? So here is some mutual coupling going on. A voltage, right? Times a current on side 1. So that means there will be some some stored energy going on inside 1, even though there's no change in current here, but it will be due to the change in current on the number 2 side. Here's just what's happening on the number 2 side all by itself. So here is that expanded now. We put in Di2. We got this mutual coupling from the number 2 side back to the number 1 side. And we're substituting now in for the voltage on the second side. And this we are going to want to find the work for, so we integrate all of that. And that means we now have what? M12, the mutual coupling, times the current on the number 1 side. But this is steady, not time changing, so it's a constant value there at I1. All right, and we're going to be integrating I2 from 0 to I2. And the same thing is going to happen with the second part of the integral. I2 is going to be integrated from 0 to I2, right? And we're going to get this. So here is some energy contributed on the number 1 side as a function. So this is mutual energy. And here is the self energy. All right. So now what have we got in all of it? In the end here now, in the third stage, I2 is going to be flat, I1 is going to be flat. So there is no di dt going on anymore, right? Di dt, whoops, is 0 there and there. All right. So now let's look at what have we got in total going on here. We want to sum the work involved. That's just the sum of the two because we were careful to make them 3 distinct regions where the time effects of the number 2 side did not affect the number 1, and then the time, so they were isolated, the time effects in the regions. And if we add those, we just simply get this straightforward. Now remember, we have only analyzed the circuit here. Where's my pen? Whoops. We've only analyzed the circuit here kind of in this one direction, right? We've started with this side and moved to this side and then moved to no change in either side. So this whole analysis, of course, could go the other way, and we'll get to that. So I'm just cleaning this up to say so far the work in this first phase analysis was simply the combination of what? The two self-inductances, which we'd expect, but now this mutual term. Okay? So we'd expect these two, but now we have this mutual term to contend with. Okay? And if the possibility exists that M12 is the same as M21, in other words, this was the work done going the other way, right? Where is my pen? So this item here, this whole equation is done as though, you know, we reversed we reversed regions 1 and 2. You know, region 1 became 2 and 2 became 1. In other words, we started with I1 being 0 and I2 changing and vice versa. So that means the mutual coupling goes in the other direction, and we reflect that in this subscript here, right, this guy. So the equations look identical is the point here, and they would be identical provided these two are identical. And we're going to say for the moment that they are. We'll be able to show later that they are. You might expect that because what the physical properties of the coupling haven't changed as a result of the current flow or the analysis direction. So we're just going to label them as M right now. All right? And so here is that summation in the forward direction. But what if the dots what if these dots up here, what if this one wasn't there and it was down here, right? What would that do for us? Well, we'd go through all the same analysis and we'd end up here with a negative sign, right? The mutual coupling would be different. The self term would not be different, even though the current and voltage are now in opposing directions, because you end up with the squared. Okay, it's only going to be the mutual that is going to inherit the minus sign, because these are just the two individual currents, right? Okay, it turns out we can just call these two. We write a simple equation going in the capturing both of this by just saying, all right, for the moment we're going to say these are plus and minus terms down here, right? These, we'll just capture them as plus and minus, but the mutual inductance is common. Okay. All right, moving on to looking at the net energy, because we're going to try to discover a little bit more about this mutual inductance and some limits and relationships. So we take our formula that we ended with in the last page, where we have clearly the sum of the self energies, right? You had this from way back in first semester, and then we add this mutual term in here, and we showed that whether you calculate this equation with the number one side driven and the number two side open, or you do the analysis in reverse, you get the very same number. And so whether the mutual coupling is considered as a side 1 to side 2 or a side 2 to side 1, we still end up with the relationship M12 equals M21, and we might as well just give that the label M, right? So that's what we're saying here. And now our only question is, the minus sign, recall, enters when the dot convention puts the dots in opposition to each other. All right, now we want to continue on to try to find some limits here around M. What are the values that M can attain? And the one thing we know, like the phrase says, the energy can't be negative. So all we need to explore is, when does this minus sign take effect to the point where this term would overcome the sums of the two energies here? All right, so we'll just express that idea in this mathematical form by simply saying the only time we're at risk is with the minus sign. And if this whole sum of stored energy is greater than or equal to 0, which it will be, has to be, then we just need to solve for when does this become a problem. When might this override the self-storage terms? All right. The book suggests this thing called completing the square, and I'm going to go through it. It's only a few steps, because it's a good mathematical technique, irrespective of this one particular problem. It's a good mathematical technique to have in your bag of tricks. So you know there's a lot of ways you can change equations to look like something you want to work with. You can multiply and divide by the same number. You can multiply both sides of an equation by the same number. That's sort of a variation on the same thing. And another one is you can add and subtract the same number to one side of an equation. And we're going to do that by adding and subtracting this value in here. So I'm going to deal with the subtract term first, since that's the one that's the reason for it. And you notice if we take 1/2, and I'm going to write this a little carefully here, right? 1/2 times Li squared, L1 I1 squared, plus, and now I'm going to bring in my, I'm sorry, I should have put in minus. I'm going to bring in my minus term, only I'm going to call it um, minus 2 because I'm multiplying by a half. So I'm going to call it minus 2 I1 I2 square root of L1 L2, and then add back in the other L2 I2 squared, right? So I'm just dealing with that first pair of terms. That's all I'm dealing with. These guys I'm talking about over here. Okay, and so what I'm going to take advantage of, obviously, is the fact that I now have something that looks like, right, 1/2 times what? L1 times the square root of L1, I'm sorry, I1 times the square root of L1 minus I2 times the square root of L2 squared, right? So if I square this term, if I square this term, I get that. If I square this term, I get that. And if I do the cross product and double it, I get that. Okay? So that's a nice squared term. So now, if I go back and put together my other piece, where I say now I subtracted that amount, now I need to add it into that side of the equation. All right, I can do that. And cleaning it all up, here I've added, here's that same term being added now. So I factored out the I1, I2. Here was my original m, and now here's the additive term. So I have all this in a straightforward way. And what I can observe, the whole reason we did this, completing the square, was we created a square so that no matter what the values of I1 and I2 are or anything else, this is always positive. Okay? So that is never going to drive us to be negative. All we need to worry about, this part is always positive. What we really need to worry about is this m guy. And in fact, what it comes down to is this term needs to be greater than or equal to 0. Okay? That is the name of the game. And so we express that. Here we are with that expressed. Just got to keep that thing greater than or equal to 0. This is relatively simple. With the m hanging there with a big minus sign in front of it, we just simply clean up the equation or the inequality and say that m has to be less than the square root of the product of the self-inductances. Okay? And in some maybe intuitive way or strange way, that makes sense. We might be able to think of some statements around this, though. You could ask yourself, is m going to be greater than L1 or L2? Okay, and the answer is no. All right. If I just took the greater one and squared it and then took the square root of it, I would have equal to that, right? So m is never going to be greater than L1 or L1. Whoops, this should be and L2. No, I had that right. It should never be greater than either one. The largest. Let me say this. It should never be greater than the largest of L1 and L2. Okay, sorry for all that, but that's... So, no, it will never be greater than the largest. So, why do I make a point of that? These are the little things that you can observe in doing the math, that when you get in the lab or when you get in a real situation or when you get in a problem-solving situation, let's say you have to solve for m or and you're only given part of the variables, there's some sanity checks built in. When you get done with something, you should be able to look, does that make sense? This is one of those things to have in your pocket that says, it's greater than the smaller one. It's probably going to be in between them all the time, right? So you just keep that in mind. We define now a coefficient of coupling K. Call that the coefficient of coupling, and it's just expressing the ratio, right? And what it tells you is that K is always less than or equal to 1. If L1 and L2 were equal, right, then M would be equal to that item, and it would be, L1 over L1 or L2 over L2. It's always going to be greater than or equal to 0. And unless one of them is 0, it's really going to be strictly greater, right? Okay, so this is an efficiency or an effectiveness number, something like that. And it automatically tells you something about the physics of it that we can expect. The higher this number, the closer it is to 1, the better the coupling, and the more each coil, each self-inductance coil is going to affect the other one. And we want that to happen. Okay? So this means our M is just whatever this efficiency is, or effectiveness, times the square root of the product of the coils. Okay? So just some things to be watching for, because now we're going to turn and we're going to look at how does that efficiency, how does that coupling manifest itself in a productive way. All right. This is a recap of the picture. We saw this earlier where we had all of the flux coming out or generated in the L1 coil, and we partitioned it into two parts, the flux that stays within the L1 coil only, and the flux that ends up also intersecting or tending to the L2 side over here. Okay? And we can then, from what we just saw, describe the coupling coefficient as how much of the stuff, how much of the flux gets connected to the number 2 from number 1 to number 2 side as a function of all of the flux available. Right? And this picture helps illustrate the more of it we can get over here, the more of it we can get from the 1 side to couple to the 2 side, the higher this coupling efficiency is going to be, and the more interaction, the greater the mutual coupling. So expressed in terms of what's illustrated in the picture, we have this is the total flux generated in the self-inductance coil L1, and then this is the amount that connects across. Reverse the whole argument and it goes the other way. The total over 2, which is these two, if I only operated the second side and left the first side open, divided by the amount that couples from the second side back to the first side. Okay, so that's our efficiency. Now, how would we physically achieve this? And that's what we're going to explore as we move forward with, as we build certain structures. What are we going to have? This illustration out of the book is kind of interesting. It has this simple comment that this could be an air or a ferrite core, iron, of course, and I'm sure you all know iron is going to be a much better, much higher coupling coefficient than air. In the same way that in capacitors, something other than air is a better dielectric. But this is actually reminds me of like an empty the core of a roll of toilet paper, and you can actually do this. Take some simple wire. The nice thing about this is you've got the coils are separated. Here's one up here and another down here, right? So this is maybe the number 1 coil. This is the number 2 coil, and you can imagine if I activate one, right, it's going to have loops going around like this. Going to have magnetic field loops going around like this. And if I activate 2, or if I let 2 interact, you can see here physically only the far-reaching loops are actually going to connect, right? Some small fraction are actually going to connect the number 1 coil with the number 2 coil in this arrangement. The stronger magnetic fields are going to stay closer to the coil in this arrangement. They always do. And in this arrangement, the weaker ones, or the ones that have to reach the farthest, are the ones that are going to intersect too. So the coupling of that arrangement is going to be, just by inspection, kind of low. Because these two terms that we talked about, Phi12 and or Phi21, are going to be a small portion, right? You can just see that physically. Using the same structure, I'm glad he took a moment to illustrate this. Using the same structure, my toilet paper roll here, if I simply wound the coils on top of each other, then everything that is generated on the, the Phi1 side is going to get coupled, or likely get coupled, into the Phi12 side, right? Because it intersects. Here, if I make such a loop, you can easily see them intersecting. All right. So that's all right. This I'll just indicate as a Phi12. So you can see this one, this guy here, is going to be more efficient. K of this one, K of the double, I'll call it, is going to be greater than K of the single one, the non-overlapping coils. All right, really just by inspection. I don't think that's anything. So obviously, when we move now to more interesting or sophisticated forms, if you will, of mutually coupled coils, such as we're going to experience with transformers, we're going to want to do arrangements that drive our K as high as possible. And maybe we wind the coils over each other like this. We certainly want the best possible cores that are going to connect them, and so forth. So that's where we're going to head with that. All right, and before we move to transformers, let's just do one of the practice problems here. The authors do an example problem, 13.3, which I'm not going to go through here on the video because they actually do quite a good job of it, quite an extensive job, as they often do with their examples. So unless there's something specific to point out, I'm not going to do that. And this is one of those cases. So here we have this circuit figure. We can look right off at some common sense things here. Here's our mutual inductance, and it is specified, and in line with common sense. It is less than the greatest of the two, right? And also greater than the smallest. All right. So what are they asking for? Determine the coupling coefficient. Well, that should be pretty easy, right? Our K is our mutual over the square root of L1, L2. So filling in the numbers, it's 1 over the square root of 2, which is 0.707. Okay? Now it wants to know, at time 1.5 seconds, how much energy is stored in the coupled pair, and we're using this for a source, right? So what do we got? We've got a frequency. Now they've given us henries. I got to go back and reset my pen. So they've given us henries. Here's our what? What is this? This is omega. We're going to need that because these things are going to have to be turned into, probably our j omega t's and stuff like that. So if omega equals 2, so at omega equals 2, let's just get some numbers in front of us. Omega t is equal to 3. Okay, so we're going to want to plug that in. And this is what? 3 radians, right? And I'm going to say, because I looked it up, it's about 172 degrees if we need that. Okay, so let's find our currents. We got to find the currents using mesh. I will. Okay, so on the left, we've got 0 degrees phase angle, but even if it was, we'd probably leave it out. So we've got 100 minus, let's have our, where's our pen? In the usual way here, I1 and I2. Our one Henry, we've got 1/8 farad and our 4 ohms, so we can go easily to that, minus 4 I1. Now we're going to want to know with 1/8, what's our j omega, right? J omega times, so I'm just going to write it like this. I got 1 over j omega was 2 times our capacitance, which is 1/8 I1. And then I'm going to have, I have the 2 Henry. So that's going to experience I1. This will be J. Omega is 2 times 2 Henrys, I1. And now I've got the current I2, right? Or I'm sorry, I've got, the current I2 coupled back through 1 Henry. But because of the dots, the orientation of the dots, this will be plus in my mesh equation. All right, so that'll be plus j omega times 1 Henry times I2, right, equals 0. That's our left-hand mesh equation. Let's do it on the right. We can start with the resistor. Actually, let's keep the I1 terms together and then the I2 terms. We can start with the mutual inductance to begin with. And that will be a similar term, so it'll be plus J2. I'm looking at this over here and saying I got basically the same thing, times 1 only now times I1. All right, minus J, the frequency omega. And now we're looking at what? The self-inductance term times 1 times I2 and minus 2 from the resistor, I2 equals 0. Okay? So now it's just a matter of how do you want to solve this? And we can go for solving, we can solve the second. Let's see. I'm going to do it first. I'm going to reduce these. So here's the first equation. And I'm going to gather terms. And it's 100 minus 4I1. That's the real terms. Minus 4I1. Remember, this is the part you need to be real cautious because it's where you can make the easiest mistakes. Here's this whole thing. So this is going to be what? Minus, this whole thing will be minus minus 2/8, so this will be 4 over j, and if I multiply by j over j, so this will just be a plus 4. We want to be careful here. If this gets multiplied by this becomes 4, j over j will become a minus j, j over j will be a minus j. Yeah, that's what I want. So 4 is going to be the number, and will be j over j, so that'll be a minus j squared. So this will all end up a plus j4. And here we've got, right, j for I1. And this will be a minus j4 I1, and then plus j2 I2. So that's going to all come down to the j I1 terms are going to disappear. Oh, is this pleasant? And minus 2 I2, j2 I2. No, this outside term plus j2 I2 equals 0. So that's the first equation. That really comes out handy. And the second equation, reduced, looks, well, that doesn't reduce a whole lot, right? So we can just solve it straight away. It's these terms directly. So we'll have what? J1, J I1. I'm just going to divide all of this through by 2, right? So I'll just divide it by 2, put a note here, divide it by 2. So I'll just have JI1 is equal to, it looks like 1 plus J times I2. All right. And if we want to solve for I1 in terms of I1, we just have to divide by J, right? So if we divide by J, I will end up with, actually, kind of interestingly, 1 minus J times I2, right? The J times this becomes, if I multiply by minus J, so this will be multiply by minus J. And you end up with that. You'll get the 1 turns into a minus J, and this turns into a minus J squared, so plus 1. Yes, that's good. So now we have that. And now by substituting, so we just substitute. What have we got? We get 100. Where am I at? We get 100, and I want to plug in for I1. I've got 100 minus 4 times 1 minus J I2 plus J I2, J2 I2. Yeah. Substitute into number 1. J2 I2 equals 0, so we still have all that going on. And if we do all the reduction here, what do we get? We get 100. Combine all this stuff plus I2 times what? This is minus 4 plus 4 JI2. So it looks like minus, keeping it easy, minus 4 plus J6 I2 equals 0. And if we go through the trouble on this, we will get I2, whoops, where am I at here? I2 is equal to 100. We just have to watch our signs real carefully. Over, I'm going to reverse it now, 4 minus J6. Woo. J6 is equal to 100 over, we know this is a little over 7.2, a little over 7. And this angle now is negative, so that's minus 65.6 degrees or something like that. Right, so I2 will be some number that we like, 100 divided by 7, so it's a little less than 14, 13.9 at a positive angle of 65.6 degrees. And I think he's probably got Well, it's not quite that. What is actually wanted? The energy stored. So we have only one part of this. All right, sorry, I'm going to have to move on. We've got stored energy here, so that's that current. We'll solve quickly here for I1 is just plugging back in, and I1 is 1 minus J. Whoops, where did we have it? 1 minus J up there times I2. And I'll shorten this number since this is just the math. And that comes out as 19.64 at an angle of 1756. Right, so we have that. That's just cranking through items. This one over here, but you remember is this is a nice 45-degree angle. So no problem there. Now, all we have to do is find the I, right? You have to finally the currents at 1.5 seconds, all right, which are the 3 radians. Remember, that's my 172 degrees, all right? And these come out to, I will just give you these rather than punch onto a new page. You're going to be plugging into something like this. I'll do one. I1 is equal to the 19.64. Take that. You're just evaluating, or 65, something like 19.64. I'm just going to take this and evaluate it at the proper point. So 19.64 cosine. And now omega t is our 172 degrees plus 1756 degrees, right? And I'm just going to tell you that number comes out to minus 1938, right? And are we surprised at this? Look, 1938 is very close to 1964. And why is that? That's because this angle is almost 180 degrees. So it's really just a sign shift from plus to minus, almost. Okay? I will tell you without sitting here and doing the math that I2 follows the same pattern and comes out to be minus 10.63. Okay. So now let me segue, since I need a little bit of blank paper. I'll finish the job up here, right where the work now is what? It's a lot more plugging and chugging. 1/2 L1, which is 2, times, and we never worried about those minus signs, of course, because they are going to be squared, plus 1/2 L2, which is a 1, times 10.63. Whoop, let's see, many squiggles. Squared, plus our mutual term. Oh, is this plus or is this minus? Right? Is this plus or is this a minus sum to the work? Well, our dots are in the opposing direction, right? So this is going to be a minus. Our m, which is 1, times the product of the currents. So that's minus 1963 minus 10.63, right? So let's just look at the contributions here. The term here is evaluates to 376. The next term evaluates to approximately 57. I'm just rounding off, which you can guess. 10, this is going to be a little over 100, and half of that is something about 50. So we know that's going to be good. And the final term here evaluates to about 206. And if I sum those up, what have I got? 376 plus 57. Well, I could take 376 minus 206, and that would be 370. 170 plus 57 looks like about 227. So I'm just going to say it's approximately 227 joules, something like that. So without cranking through, they say it's a little higher than that, but I'm sure if I kept track of all my details and fractions here and there, I'd come out about the same. So that is practice problem 13.3. All right, so that's completing those sections through 13.3. And next time in part 3 of the chapter 13 lectures, we'll take up transformers, linear and ideal transformers, and then possibly autotransformers, which are just a simple case of ideal transformers. So, till next time.